the lecture. On Wednesday, we won't have any lecture. But on Wednesday, we will discuss about the midterm questions. I will also upload the solutions of the questions of the midterm, today or tomorrow. So any questions before we start? Not related with the midterm questions.
Exam dates, you said you will.
Okay. So when should we do the next exam? Last week of December. Well, let me check the dates.
Hafta galiba sınav var. Yani aynı gün olur.
Okay, so the options.
No,
28.
otomatik böyle değil.
Okay, so 21st.
Or 28 is not, 28 is not possible.
So you have an exam on 28.
Do we? 28 is long.
Only possible days are Saturdays or Sundays.
Well, I mean, if it is the weekend, so we can extend the duration of the exam.
Can't we go to January? Like, should it be on?
Come on, that is the last week, no? So at least we should be covering a few more topics before the final.
So 8th of the January is the last day?
I think so.
14?
14 is too close.
21st is almost 1 month from now. Okay.
Same thing in the afternoon.
Just like this one. Okay, so last week we looked at the quantum mechanical description of statistics. Well, the lessons we have learned was we can basically keep doing what we had done before with the Boltzmannian factors, etc. The important distinction would be these NIs, the so-called occupation numbers, how many particles are in the state I. In the Maxwell-Boltzmann case, we just said that, okay, exchanging them gives us new states. But in the quantum mechanical case, if they are indistinguishable particles, in that case, this NIs specifies the microstate uniquely. So somehow we need to deal with this fact. So when we are counting the number of states that corresponds to a given macrostate, we have to be able to count the number of different sets Ni. So that will be our task. So let's start with the microcanonical. Now we will be discussing simple gases. Now let's start with the microcanonical ensemble. Now, if you remember, in the microcanonical ensemble, what we do is E is fixed, N is fixed, V is fixed. So we are trying to count the number of microstates corresponding to these macrostate. Now, if I have the set Ni, then these Ni's should satisfy sum of Ni should be equal to N, I being the single particle state. And at the same time, sum over epsilon I and I should be equal to E. These are fixed. So we need to count the number of Ni's that satisfy these two conditions. Omega is the number of distinct sets Ni. And each one of these ni's corresponds to a different microstate. Now, for example, let's say that we have all these single particle states with various energies. I have, let's say, 2 particles over here, 1 over here, 3 over here. So this is N0 is equal to 2, N1 is equal to 1, N2 is equal to 1, N3 is equal to 3. Or you can just put as many particles as you want. Now, since the total number of, okay, let's say that, suppose we have one such set Ni. And we can imagine these different energy levels with different number of particles. I can obtain a different set by just changing these dots among these states. For example, I can just move this dot up to over here. If I just consider moving dots around, then this condition is automatically satisfied. Remember, I want to find the sets such that they satisfy those 2 conditions. Okay, just put n dots along on these lines. You just move them around, and different ways of moving them around gives you different sets Ni. So you can just, that is one way of obtaining different sets Ni. But there is a second constraint which will make our life a lot difficult. Because you see, if I move this particle to a higher energy state, the total sum should be constant. So other particles, I should move them to lower energy states. For example, I should move this one down and also this one down to obtain a new set of Ni.
Can I ask something? But this is related to an old homework that I had the problem, the last homework. So in that homework, can I ask this or? Okay. In this homework, there is this quantum system, a 2-level quantum system, 2 energy levels and 1 and 2. And the total number of particles is fixed. And this is connected to a heat reservoir. But it doesn't say if it's in an equilibrium or anything. And to solve
all the questions we are discussing will be in equilibrium. So
yes, I assume. But then it says, the question says, there is a quantum process which takes one particle from one level to the other level, and then we had to derive some thermodynamic relations. But I thought we were supposed to use the canonical ensemble because there is this heat reservoir. But then this question becomes unsolvable. But writing these 2 conditions, now it makes me think that we should be writing a microcanonical ensemble because the energy is fixed. So is this how we decide which ensemble to use then?
You see, in this problem, since we started with the microcanonical ensemble, energy is fixed. Given a problem, you see, what we had done was in the canonical ensemble, we are allowing the energy to fluctuate, to change. But we had also calculated the fluctuations, and we had seen that the fluctuations are negligible. So basically, whether you use the canonical ensemble with a given temperature and calculate the average energy, or the microcanonical ensemble, where the energy is fixed to be equal to the average energy in the canonical ensemble, you should get exactly the same answer. In fact, here we are also going to show basically the same idea. So we are looking at a system. Such a system, we will derive certain properties of these systems, and we will explicitly show that whether you use the microcanonical ensemble or the grand canonical ensemble, you get exactly the same answer.
So yeah, I have to fix the energy.
But if you are saying that you are looking at the microcanonical ensemble, then you are fixing the energy. That's what you are saying. If you are saying that, okay, you will study this problem in the canonical ensemble, then you are fixing the temperature. If the problem gives you the energy, you can still treat it in the canonical ensemble because the fluctuations will be negligible. But eventually you have to calculate the temperature in terms of the given energy of the problem.
Yes, but I was thinking that if there is a quantum process that takes one particle to another energy level, and now we are far from equilibrium, right? And the temperature of the system...
No, you see, you can basically think, in that problem, you can think that, okay, initially you are in equilibrium.
Yes.
something happens
Yes.
during which the system is not in equilibrium. In the final state, it's still in equilibrium. You can still treat the problem as if the system had been in equilibrium, both in the initial state and also in the final state. That is what we call the quasi-equilibrium.
Yeah, maybe I should ask this in the break because
You said that the energy is fixed, and for example, if the lower state one is going to the upper states, it gains energy, right? So some other ones
Should go down.
But how can we be sure about the difference is equal to zero?
We have to make sure, I mean, you see, the problem is, let's say that I have one set of Ni. How can I obtain the other n sets Ni? So one way is just moving them around, move one particle to an excited state, and of course we have to move some other particles to lower energy states, making sure that the energy is fixed.
But
And then we have to count in how many ways we can do that.
we need lots of particles to do that.
Sure, we have infinitely many particles eventually.
Yes,
And also keep in mind that the
so
energy
this way
levels. Huh?
It's possible. This way it's possible. Infinite number of particles. Because if it was limited,
Well, you see, the number of particles we have is always 10 to the power 23 of that order of magnitude.
yes. But what I mean is, if the particle number was much less, there are less ways to do that. So
Sure.
probably it will not.
So
be possible.
we are trying to count the number of ways. It can be a small number, it can be a large number. The idea is we should be somehow trying to count the number of ways we can do this. We can just move these particles around, keeping the constraint fit, still satisfying the constraints. So if I can count the number of ways in which I can shuffle these particles, then I know the number of sets Ni that satisfy those two conditions, which is still not an easy task.
And you said that we can call, if we have two states which are finite initial states which are equilibrium, we can call it as quasi-equilibrium, right?
Yeah.
But I thought that quasi-equilibrium is something feature for the process. Even if we don't know the process and the system is not in equilibrium during the process, we can call it as quasi-equilibrium.
Yeah, quasi-equilibrium is a system which can be treated as if it is in equilibrium. For example, for short intervals, okay, this room is not equilibrium. The temperature will be constantly changing. But if I study this room during, let's say, 2 minutes, I can treat this room as if it is in equilibrium. That is a kind of a quasi-equilibrium process. Or you can say that, well, there's some heat exchange between the outside and inside. There is some temperature gradient between the window and where I sit. If I take small enough slices, in each slice, I can define a temperature, more or less a uniform temperature. I can say each slice is in equilibrium also. That's also a quasi-equilibrium. Not exactly equilibrium, but I can still treat it as if it is in equilibrium. Okay, back here. Now, this counting the number of ways of shuffling all these and particles among various states, counting them will be highly complicated. So I will make many approximations. I will introduce many errors in calculating this omega, but we had already seen that, I mean, even if I miss omega by a factor of, 10,000, that will be negligible. The effects will be negligible. I can just ignore it. Now, the difficulty in shuffling these, as your friend pointed out, if one particle moves to a higher energy state, how many particles should I go to a lower energy state? So that will be kind of difficult to count. But what I will count is how many different states I can move this particle to. I just move that particle and nothing else, so that this condition is almost satisfied. remember in our discussions about this microcanonical ensemble, even there we said that, okay, saying that energy has this definite value is not so realistic. So what we had done was, this is within some uncertainty. So what I will do is, rather than allowing all kinds of shifts, I will divide my states into groups. So let's say there is a group over there, there's another group over there, there's another group over there. I'm just grouping states that have energies very close to each other. Now, let's say that in your book these are called cells. Let's say this is the ith cell. I have many cells. And let's say that in ith cell there are GI states in ith cell. And Ni this time will be the number of particles in one of the states in ith cell. And okay, you see, here I called Ni to be the number of particles in the state I. Now I'm slightly changing its definition, and I here is now the number of particles in one of the states in the ith cell. So it can be in any one of those states. The conditions the Ni's should satisfy are still sum of Ni is N, sum of Ni epsilon I should be equal to E, where epsilon I is the energy of one of the states in ith cell. Still the same constraints. Which one? Well, they all more or less have the same energy. And keep in mind that since the energy spacing goes as 1 over the size of the system, within a very small energy range, I can have a very large number of states. In fact, in the limit that n goes to infinity, the number of particles goes to infinity, all these GIs will also go to infinity. So now, if I take the ith cell, there are GI states here. Now the question is, in how many ways can I distribute Ni particles in GI states? You see, because if I take one particle from this state in the ith cell to this state in the ith cell, okay, the total energy will change, but the change will be proportional to the width of the energies of the ith cell, which I assume to be small. So if I move one particle from one state to another state in the same cell, this condition is not modified. This condition is still satisfied. This doesn't count all the sets Ni, because in principle there are also shufflings where one particle moves to another cell and some other particle moves to lower energy cells, let's say. There are also such distributions Ni. I'm ignoring them. I'm assuming that the number of such different Ni's will be negligible compared to what I will obtain over here. That's an assumption which turns out to give the correct answer. As I said, I'm introducing an error which hopefully brings a factor that is less than 10 to the power 5. Because even if I just take 1 in 10 to the power 5 states, even if I just count one state in 10 to the power 5 states, well, it gives me the same answer at the end. So, of course, now, if we have bosons or fermions, they will behave differently. Now, if I look at fermions, since their wave function had to be antisymmetric, there can be at most one particle in each state. I have GI states. I have to select Ni of them and just put one particle in each one of those Ni states. This is GI factorial. This is divided by Ni factorial, GI minus Ni factorial. So for a given Ni, there are this many microstates corresponding to different arrangements of these Ni particles between the states of GI, state of the cells in the ith cell. Questions? You all look puzzled. You all look puzzled.
Hocam, so we neglecting the small energy differences, right?
Yes. We are saying that the energy doesn't have a fixed, definite, single value. There's an uncertainty in the energy.
Since there is lots of particles, so if we are taking care of one particle, a huge energy difference still can be neglected, right?
Well, you see, since I'm counting the number of states, I'm already ignoring many states, many microstates corresponding to a given macrostate. Your friend is right. Your friend is claiming that in each cell there is an energy uncertainty. So if you just move all the particles in the lower energy states to the higher energy states, since you have many cells, and if you do the same thing in all the cells, although the change in the energy due to the moving one particle from a low energy state to a high energy state is negligible, if you do this thing in all the cells, you will get a significant change in the energy, right? But the number of sets Ni that will be obtained in this way will be very small.
Yes.
And plus, since I'm already ignoring many sets Ni, by taking these states into account, I'm adding some more. So on one hand, I'm reducing the number of possible sets by ignoring the shuffling of particles between different cells. On the other hand, I'm adding some more sets Ni by taking such shufflings into account. So it makes my argument even better, not worse. Because I'm subtracting some, adding some more, they cancel
So is it
to some extent.
doing some kind of thing is decreasing the probability of this thing happening, shuffling?
I'm not talking about any probabilities at the moment.
No, what I mean is the lowest probability maybe means
The number of
less
states, there are few number of states obtained in this way. So even if I add them, they won't change significantly total number of microstates corresponding to my given macrostate. Let's see what happens in the case of bosons. Let me call this omega I. In the case of bosons, now the question is, I have Ni particles I have to divide this GI groups. I have GI sets, Ni particles. I have to just distribute these Ni particles in all these GI sets. But this is just like the problem of the many harmonic oscillators we have. Let's say that if you remember what we had done in the case of harmonic oscillators, we said let's have capital N harmonic oscillators, each one having the quantum number N1, N2, etc. the total energy was E. So we have to divide N1 E quantum numbers, E quantum of oscillator into N oscillators. The total energy is E. We have to divide this E into N oscillators. This is exactly the same problem here. Instead of E, I have Ni. That's the total number of particles I have. I have to divide this into GI groups. And if you remember what we had done in the case of the oscillator, we just imagine separators. GI minus 1 separators. So each ordering of these Ni particles and GI minus 1 separators gave us, also in this case, gives us a new microstate of this cell. So this will be Ni plus GI minus 1 factorial. If I exchange these dots, nothing changes. If I exchange these separators, again, nothing changes. Let me also write the Maxwell-Boltzmann case, what we had done up to now. Now, each one of these particles, Ni particles, can be, now this is Bose-Einstein, in GI states. So if there are Ni of them, it is GI to the power Ni. But then if I just exchange the particles in the Ni state among themselves, nothing changes. No, sorry. Yeah. No. No. Let me come back to that point later on. Now, the total number of microstates corresponding to a set Ni, again I repeat, if you identify Ni as the number of particles in the ith state, this is just one. Because if you know the number of particles in each single particle state, that uniquely specifies your microstate. But here these Ni's are the number of particles in my cells. So corresponding to a given set Ni, this number is product over I of omega of I. Whether you use, if you have bosons, you have to use this factor omega. If you have fermions, you have to use this omega. But whichever omega you use, because basically what I'm doing over here is I have these many cells. The number of microstates of the combined cell system is, well, if the first cell can be in 5 different states, the second cell can be in 4 different states, the combined 2-cell system can be in 5 times 4, 20 different microstates. So I'm just multiplying them. Now, in the case of Maxwell-Boltzmann distribution, this omega would have been n factorial. Just, I shuffle them all. Divided by ni factorial. In each cell, there is gi to the power ni. This would have been the Maxwell-Boltzmann distribution. Well, if I also take into account the Gibbs correction, 1 over n factorial. So this is product over I, gi to the ni divided by ni factorial. Now, omega, the number of microstates that I'm looking for, would be sum over all sets Ni that satisfy my constraints of this omega Ni, whatever your statistics is. Entropy over k would be just logarithm of omega, which will be logarithm of Ni factor of this sum Now I will use the fact that I'm dealing with huge numbers over there. These omega and i's are huge. You see, since in the thermodynamic limit, even within a very small range of energies, which will be my cell, the number of states will be enormous. So this sum can be approximated by the largest element in that sum. Now the next task is, what is that largest element?
Can I ask a stupid question? So, I know that the Maxwell-Boltzmann distribution is different than the Bose-Einstein, but I fail to remember this difference between the two particles that we deal with. Because because after you introduce the Gibbs correction factor, they seem like they're the same. They're indistinguishable. They exchange and.
Yeah, you see, the problem is classical physics tells us that all the particles are, even if they are identical, they are distinguishable. So we have n factorial divided by ni factorial different states corresponding to the quantum numbers ni. Okay. Now, Gibbs correction, but quantum mechanics tells me that for a given quantum number ni, the number of microstates is 1. This is Maxwell-Boltzmann. In quantum mechanics, it is 1 or 0. Now, Gibbs correction divides this by n factorial. Still, it doesn't become indistinguishable because still it doesn't become 1. That is the main difference between Maxwell-Boltzmann and the Fermi-Dirac or Bose-Einstein statistics. It does make some correction, but not everything is correct. So still the particles didn't become indistinguishable after incorporating the Gibbs correction. We will see under which conditions they will be equivalent. But you see, keep in mind that 0 factorial is equal to 1, 1 factorial is equal to 1. It's kind of Maxwell-Boltzmann distribution becomes the quantum mechanical distributions if the number of particles in a given state is around 0 or 1. We will see that if it goes to 0, in that case, they are equivalent. Okay, well, let's just go over this problem. I have a problem of finding, if I have n particles, if I know I know the macrostate. I'm trying to find the microstates corresponding to the given macrostate. So that will be finding these sets Ni that satisfy these two conditions. Now, one way of obtaining these different sets Ni, just start from one distribution of Ni that is allowed. So it's just place the particles into their various states and then shuffle them around. Subject to, well, if you just shuffle the particles around, you are already satisfying this constraint. You have to be a bit careful about satisfying the energy constraint. So if you just move one particle to a higher energy state, you have to make sure that you move some other particle to lower energy states. It can be one particle or more than one particle. That's kind of a tough problem to solve. So rather than doing that, what I'm saying is, okay, rather than looking at all these shufflings of these particles, I will only shuffle within a very narrow range of energies. Given one particle, I won't move that particle to a very high energy state. I will just move it to a state that is nearby in energy. If I move that around, I still lie within this uncertainty range. So if I just move my particle to a nearby energy state, okay, I satisfy this first condition automatically, but the second condition is also satisfied. So now I'm asking the question that, given some distribution, in how many ways I can just move them around to nearby states?
This is the same thing as decreasing the size of the cell, right?
No, I'm already, well,
Because we're not counting inter-cell blocks. Like you can't go from one cell to another.
no, I'm not allowing that because then I will not be able to satisfy this condition without some other particle going to some other state. And then I just made a small change in my notation, and I now is the number of particles in a given cell. Not the number of particles in the ith state, is Ni becomes the number of particles in the ith cell. Since in a given cell there are still many single particle states, there are many microstates corresponding to a given Ni. Then I just counted the number of microstates corresponding to an microstates of a cell corresponding to an Ni, because I'm allowed to move my particles within the cell freely. And if I move my particles within the cell freely, then these two conditions are automatically satisfied. So for bosons, well, this is the number of ways in which I can just place Ni particles in Gi states. For fermions, well, since there is a single part, there can be at most a single particle in each state, it's enough to choose Ni states among Gi states. So once I choose Ni states, I just put one particle in each one. Which particle I put in which one? Well, I don't care because they are indistinguishable. It doesn't matter. And then the total number of microstates corresponding to these numbers Ni's is given by just the product of these, product of the number of microstates corresponding to each cell. And that kind of gives me, this is the number of microstates corresponding to the set Ni, where I repeat, Ni is the number of particles in the state in the cell I. Now, each one of these numbers, keep in mind that Gi is the number of states in a cell. It's a huge number because in the thermodynamic limit, the spacing will be very small. So even if I just make sure that the energy spread within a cell is very small, there will be infinitely many states within that cell. That means Gi will be huge. Similarly, Ni will typically be huge. So these numbers will be huge, and hence so this number of microstates corresponding to a number Ni will be huge. Huge meaning the macroscopic. So in that case, the total number of microstates would have been given by this sum. Again, I'm making an approximation here. The total number of microstates will also involve sets in which I should also allow intercell shuffling of these particles, which I ignore them. But I'm just hoping that that doesn't introduce a huge error. So then the number of microstates will be just the sum over all sets Ni, satisfying my constraint of these factors omega. And since these are huge numbers, that sum is mainly equal to the term that that is the maximum value. I have, in that sum, I have many sets, but I don't have to calculate each one by one. There is one term in that sum that dominates that sum. And hence the entropy will be just given by the logarithm of omega evaluated at the set ni, which maximizes omega. Again, this is an error, but it won't affect the results. Now I need to find the sets ni that will maximize omega. That will be my next task. Let's start with Fermi-Dirac case. Remember, for the Fermi-Dirac case, this was equal to product over I gi factorial divided by ni factorial gi minus ni factorial. Let me take the logarithm. This is the sum of logarithm of gi factorial minus logarithm of ni factorial minus logarithm of gi minus ni factorial. I repeat, these gi's and ni's, they are huge numbers. So I can use the Stirling approximation. This is equal to I gi logarithm of gi minus ni logarithm of ni minus gi minus ni logarithm of gi minus ni. Well, let me look at the variation of this number as I change the numbers ni. Because this, when I evaluate it at the maximum value, should be 0. So this will be equal to minus variation of ni logarithm of ni minus ni times 1 over ni times the variation of ni. This is the variation of this second term. Plus variation of ni logarithm of gi minus ni plus gi minus ni 1 over gi minus ni variation of ni. So the variation of logarithm of this omega is minus the variation of ni logarithm of ni plus 1, these cancel, plus logarithm of gi minus ni, that is minus, and minus 1. Which should be 0. But I cannot just set the coefficient of that variation of ni to 0 yet, because those should also satisfy variation of ni. When I sum over them, it should be 0. This basically tells me that the sum should be constant. And at the same time, epsilon I, the variation of ni, should be 0. This is basically epsilon I, and I is equal to E, which is constant. So I have these two constraints. Well, in this case, we use the method of Lagrange multipliers. So sum over I minus the variation of ni, logarithm of ni plus, these ones also cancel. This term cancels this one. Minus logarithm of gi minus ni plus alpha epsilon I plus beta beta epsilon I plus alpha should be equal to 0. I might be changing the sign of alpha and beta later on. Now, once I add the Lagrange multipliers, I can equate the coefficient of this delta ni to be 0 for all of them. So, which tells me that logarithm of ni minus logarithm of gi minus ni plus beta epsilon I minus alpha should be equal to 0. Well, this is logarithm of n. Now this is plus beta epsilon I plus alpha should be equal to logarithm of gi over ni minus 1. So gi over ni minus 1 should be equal to the exponent of beta epsilon I plus alpha. gi over ni is 1 plus exponent of beta epsilon I plus alpha, or ni star. Well, let's see, this is 0 for ni star. Over gi is 1 over 1 plus exponent of beta epsilon I plus alpha. And we will see when we look at the canonical ensemble, beta is 1 over kt, alpha is minus mu over kt. You see, Ni is the number of particles in the ith cell, where there are Gi states. So number of particles, that's the average number of particles per state, is actually Ni star over Gi. I have Ni star particles in Gi states. The average is just divide them with each other. So the average particles in a state with energy, or we had already seen many cases where the average is nothing but the most probable or the maximum number. This is given by 1 over e to power beta epsilon times, let me just use z, z inverse plus 1, where z is okay, so yes. Does that have a so this distribution is called the Fermi-Dirac distribution. So any questions up to here? So let's give a 10-minute break then, and we will continue after the break.